Hello and welcome to the Logic webinar presentation, Fan-Out Packaging Technologies, the Past and the Future. My name is Richard Lee. I'm the Product Marketing Manager at Tech Insights. I'm here to introduce our presenter and tell you a little about Tech Insights. Today's presentation and live Q&A session will be hosted by Cameron McNeil, the process analyst and packaging subject matter expert at Tech Insights, and by Michelle Wang, who was the process analysis engineer at Tech Insights at the time of this recording. This presentation was previously recorded, but you can submit questions to be addressed during our Q&A session at the end of the webinar. Just click the question tab and enter your question in the text box. I will hand it over to Michelle and Cameron shortly, but first I'd like to provide a short introduction to Tech Insights. Tech Insights is the most trusted source of intelligence related to semiconductor innovation and the surrounding markets. By reviewing the innovation others cannot inside advanced technology products, we provide competitive technical intelligence through reverse engineering to inform product roadmaps. We offer market analysis to de-risk strategic investment and procurement decisions, and also provide IP services to clients. So why choose Tech Insights? Founded in 1989, Tech Insights offers a combination of the latest technologies and analytical techniques, knowledgeable subject matter expertise in the broadest range of technologies, and the world's largest database of semiconductor analysis created over our 30+ years of operation. We serve our global clients from the headquarters in Ottawa, Canada, as well as from a number of satellite locations around the world. Now I will turn it over to Michelle.
Introduction, and welcome everyone to this webinar on high-density fan-out package technology. And my name is Michel Roy. So today we'll be looking at the key structural elements of two recent packages that we've analyzed here at Tech Insight. So the first one is the TSMC integrated fan-out, which is called INFO, which is a high-density wafer-based fan-out package technology. The second one is the Samsung fan-out panel level package, so FOPLP, and this is a high-density panel-based fan-out package technology. Sorry. So I'll be showing some detailed package cross-section and RDL delayering image, and hopefully out of this we'll be able to make some process observation based on the key things that we've discovered through this package. So let's start. So the first section will be going through the TSMC Info POP technology, which we discovered in the Apple A10, A11, and A12 application processor package on package. So before we start with a detailed analysis, I just want to bring up some information from TSMC, which briefly go over the info process flow. So what TSMC is mentioning is that, first of all processes are carried out in a wafer format. So what this means is that, and I'll walk you through the process flow here. So basically they start with a wafer carrier, and this wafer carrier has the same size as a wafer ultimately, right? So then they pick and place all the dies, and second step is to overmold that wafer carrier entirely. Then you proceed with the copper RDL, BGA deposition, and then you reach a point where you actually debound the carrier, and basically you're obtaining what's been called a reconstituted wafer. So up to that point, this is pretty much a standard process flow in the industry. So what TSMC is adding up is this package stacking. So what this means is that the POP stacking is actually done at wafer level as well. So we'll see the detail of that in a minute. Then the last operation is dicing and shipping. Okay. One more slide before we jump into the detail. So this is showing the typical process flow used in the industry for a fan-out wafer-level package. So what we have is a phase-down die first process, face-up die first, and a phase-down die last. So phase-down die last is not very well in use in the industry, so I'll be only discussing for now the phase-down die first and face-up die first. So what all this mean? So the phase-down die first is that you start with your wafer carrier, and then you mount your die face down, which means that the active side of the die is facing or is attached to the carrier. Then you proceed with the overmolding, debonding of the carrier, and the RDL and ball attach. For the face-up process, it's the other way around. So the dies here are facing up. So the active side of the die is facing up in this case. But also, well, what we should say is that the back side of the die is attached to the carrier plate. The difference here is that you still have the overmolding process, but at this point, you're basically obscuring the contacts on the die. So you need to have a planarization process to basically expose the contact, and then you proceed with the RDL and carrier removal. So all this to say is that the TSMC info is using a face-up process, and I'll be pointing to some evidence on that during the presentation. So let's start with the real thing. So we're now looking at the POP images of the Apple A10, A11, and A12. So the top side and the back side. So the A10 was actually discovered on the iPhone 7 back in 2016, then the A11 on the iPhone 8 in 2017, and more recently on the iPhone X, the A12. So on the back side of these packages, well, there's a lot of solder balls. For instance, on the A10, there's up to 1,400 solder balls on the back side. And these little square are basically capacitor dies. So that's pretty nice features from TSMC on this. And I'll show some detail in the cross-section view in a minute. So let's move down to the first section view. So this is based on the A11 section, section. So the upper image basically is the overall section view of the POP assembly. And the two bottom image is looking at specific area. So in this case, we're looking at the two package edges. So if we look at the bottom image where my cursor is, so we can clearly see the DRAM package, which is the upper package sitting on top of the processor package. So that processor package is the one that was built with the info or the fan-out process, I should say. So what we could see on this is that, well, the copper RDL structure is visible along the backside of the package molding compound, and through the molding compound we have what we call the TMVs. So this is true mold via. So what this does is that it actually does the vertical interconnection between the copper RDL all the way up to the solder balls and then eventually through the DRAM package. So before we jump to the next slide, I just want to touch base on what I've been explaining before, that TSMC claimed that the mounting of the POP or the top package is done at wafer level. So let's find out if we can see some detail around this. So I've just highlighted here with this red line, the edges of the processor package. So if we look just above this, we have what we call the package under fill material. So I'm pointing to that edge here. So as you can see, the package under fill edge is collinear with the processor package. So that's a clear indication that when this assembly was diced, well, actually the dicing went also through the package under fill. So that's a clear indication that obviously the upper package was mounted on the bottom package prior to dicing. So this confirmed that indeed TSMC used a package on package mounting at wafer level. Okay, next slide. So we start revealing a bit more about the die area of the application processor with the molding compound surrounding the die and the copper RDL running on that structure, below that structure, sorry, I should say. Next slide. We're looking at the capacitor die, which is attached on the back side of the copper RDL. So that's a pretty neat feature from the TSMC team here. So the capacitor die is actually surface mounted on the back side of the RDL, which is where my cursor is. And they've been using very small solar ball to do that surface mounting, which are visible through the underfill. So on the right side image, that's a highly magnified view of the capacitor die. And what we can see, well, first of all, the capacitor die is a silicon base structure. And inside that substrate, we could clearly see some trenches structure. So this is basically a deep trench capacitor. That's a pretty good design. Well, this capacitor is approximately 100 microns away from the active surface of the application processor die. So for decoupling purpose, that's a pretty good approach. Okay, now we're start looking at some SEM imaging, and specifically looking at the corner, one of the corner of the application processor die. And on the right side, it's a highly magnified view of the RDL structure running underneath this. So let's start with the left image. Sorry. So the overall package thickness is 230 microns, die thickness 160. So molding compound is visible, the RDL structure underneath this. So there's a total of 5 RDL layer. So only 4 are visible at the moment, but we'll see the 5th one in a minute. So looking at the right side image, the trace width is 8 microns. So that's a pretty small feature. So that's the smallest features that we've observed on this design, by the way. Before we jump into the next slide, we can start talking about the process flow used by TSMC. So I mentioned initially that they've used a die face-up process. So in order to have this, we need 2 things. So first of all, the die backside must be mounted on a wafer carrier. So let me bring a reference line here, which is this blue line. So that mimics where the location was of this wafer carrier initially. So right below this, you see this black layer, which is labeled as an adhesive. So indeed, the back side of the application processor die was mounted to a carrier using this adhesive material. So that's the first element. Second thing that we need to consider is that after the overmolding process, well, the overmolded surface need to be planarized. So that's what we've seen initially. So let me bring another reference line. So if you look closely at the molding compound structure, so we can clearly see these nice spheres. So those are basically fillers, particles within the epoxy molding compound. And if you look closely along that reference line, well, some of these spheres have been truncated or cut off. So that's a clear, very clear indication that this surface has to be planarized somehow. So, and I'll come back to this overall process step later, but again, keep in mind that this is a face-up process. Okay, next slide. So left image is the same as what we've seen, looking at the corner of the die with the RDL structure below this. And the right side image is taken along the die surface somewhere else. So these 2 images are at the same magnification, same scale. So I just brought up here the planarized surface. So looking at the right side image, so below that planarized surface, we could observe 1, 2, 3, 4 RDL structure. And above that planarized surface, we see the missing one, well, the one that we haven't seen before. So that's the fifth one, which is the first one. So that structure is above, again, this plenarized surface. So it means that this M1 copper structure has to be deposited on the application processor die prior to the introduction into this wafer level packaging. So basically we call this M1 copper structure a pre-pattern RDL. So looking at this M1 copper, well, it looks only like a pad with a via connection down to the die surface. Well, it's more than that. Actually, I'll be presenting some RDL delayered images, and you'll see that this M1 structure actually has some trace interconnection going on between between different pads. Okay. Next slide, we're looking at the TMVs, the TMV structure. So let me bring again this reference surface, this planarized surface, which is the same surface as what we've seen before. So TMVs are essentially a large copper pillar, roughly 200 microns in diameter, which basically pierces through the whole molding compound structure. And as I said before, the whole intent of that is to basically interconnect vertically the RDL structure sitting below this up to the DRAM package, which is sitting on top. So the right side image actually show the M2 copper RDL that basically via down and contact the TMV structure. Next slide. So that's another nice features that that the TSMC guys introduced in this device. So we're looking at the right edge of the package here, which is this left image. And if you observe here at the very bottom location, so it's being labeled as an RDL guard ring. So let me bring again the planarized surface as a reference, and I'll do that also on the right side image. So that RDL guard ring was actually formed right below this planarized surface, and it's actually right below the molding compound structure. So this RDL guard ring structure is essentially running along the full perimeter of the package. So it's formed a nice ring all along the full, again, perimeter of the package. And so these via connection all the way down, so those vias are not circular via, but they are trenches via. So if you were to cut or section this package at different location, so the structure is always repeats, right? So it's pretty nice structure implemented by TSMC. Okay, so now that we have a fairly good understanding of the key structure of this package, so we'll speculate a bit and try to understand the specific process steps involved in the making of this info process or package. And this will strictly be based on the features observed on the product. So the left side image is, we've seen that before. So the application processor die with a pre-pattern RDL, the RDL below this, the molding compound, adhesive, and the top package sitting on top of this. Right side image, same magnification as the left image, looking at TMVs and the RDL. So what I'll do, I'll bring the planarized surface as a reference point, and also that blue line that we've discussed before, which is a starting point of this whole process. So what I'll do, I'll blank these two images, and we'll start. So I'll bring back some portion of these images, and we'll try to replicate the process steps. So right above that blue line, as I said, likely there was a wafer carrier, which is a starting point. So the first step will be to attach the application processor die to that wafer carrier. So obviously here we're seeing only one, but there's probably 100 of those which are attached to that wafer carrier using this adhesive. So by the way, everything is upside down here, but I guess you guys get the point. So really it's a face up process because the back side of the die is facing again the wafer carrier. The pre-pattern RDL, as you can see here, I've added up some material using this PowerPoint features. And I'll touch base on the next step here because this surface will be planarized. So what about the TMVs? So the TMVs, there's probably 1,000 of those TMVs to be placed down on the carrier. So how this thing was done, I'm not too sure about that, but one approach could be that all these TMVs were in a matrix format, which is, I guess, I'm trying to depict that with this structure underneath that. So probably the one approach is that all these TMVs are secured together somehow, and then they're dropped down on the wafer carrier. So let's take this approach for now. So the next step is to overmold the entire wafer carrier. So when I said overmold, it's actually the molding compound also flows on top of the application processor die and the TMVs. So next step, we need to planarize that surface. There we go. So now we've basically obtaining a nice clean surface, which is perfectly parallel to the wafer carrier. So we can now start the RDL patterning on that active surface and also connecting the TMVs with that RDL structure. Next step, we could actually debound or remove that wafer carrier and proceed with the POP attachment. So basically all the DRAM packages are dropped down at wafer level onto the reconstituted wafer. The packages are soldered in place, underfilled after that. And before the last steps, there's all about attachment on the back side of the package, along likely with the capacitor die, which are not visible, but it has to be mounted in the same process step as well. And finally, the dicing of the packages. So again, this is all based on the observation of the structure, and there's probably a lot of process step missing or sub-process step missing, but I guess we've captured most of them in this little presentation here. Okay, now let's move down to the planar view of the TSMC info package. So what I'm showing is the very bottom planar view of the M5 layer. So that's the very bottom layer, metal layer of the package. So basically, essentially what you have here is the BJ pads, a bunch of BJ pads with the capacitor pads essentially are seen here on that layer. Oops. Next layer down is what we call the M4 copper. So let me bring a high magnification view of some section of it. So what's going on this layer is a bunch of interconnection traces with probably like a ground plane, reference plane, or power plane going on with that structure. So by the way, these images here, these planar images are very high resolution images, and here at TechInsight, we do a lot of delayering of these packages, and we have the opportunity to do some reverse trace analysis using these layers. So that's very nice features that can be done using these images. Next layer down, M3 copper. So essentially ground plane and or power plane going on that layer with some traces, interconnection. M2 copper, This is the first fan-out RDL right underneath the application die, which start to be visible here if you follow my cursor. So again, looking at the highly magnified view of that structure, we see some nicely laid out differential trace being patterned on that surface. Nicely done here. Now we're reaching basically the planarized surface, and we're basically exposing the M1 copper structure, and also the die is also visible. So all the fan-out layers have been removed, so that's why we're seeing the TMVs surrounding the die. So if we bring a highly magnified view of that M1 copper layer, so what you could observe, yes, there's a bunch of copper pads on that, but also there's what we call this pre-pattern structure. So there's some interconnection going on at that level. So some of these pads are connected together on that very first layer or pre-pattern layer. Okay, so that's basically conclude the first part of the presentation. Now we'll be talking about the Samsung PLP panel level technology. Okay, so before we start in the detail of the section, so what's the motivation in migrating from the fan-out wafer level package to a fan-out panel level package? So as we've seen, the fan-out wafer level package is basically essentially using a wafer as a supporting or as a carrier, I should say. So for a panel level application, basically your carrier is a panel. So if you can fit so many packages on a 12-inch wafer, well, using a panel, you can fit probably 3 or 4 times the number of packages. So the whole motivation migrating to a PLP solution is to reduce your cost, your packaging cost. So just to bring some context to what this structure is before we look at the section view. So this is some extract from an IEEE paper presented by the Samsung team. So what they're mentioning is essentially that the panel level package is emerging as a most cost-effective technology featuring a large and efficient working area, which is this large panel. So compared to a 300 millimeter wafer size, about 3 times the number of units can be accommodated on in a panel, which presumably here they've been using a 500 millimeter by 400 millimeter panel, which is roughly 20 inch by 16 inches panel, which is pretty large panel. So SEMCO, which is Samsung Electronic Mechanics, which is a division of Samsung, they're saying that they've developed their own platform, and this is essentially what this whole platform is. So basically they're combining 2 different technology. First one is a substrate-based technology with an RDL regular technology. So if we look back at the substrate-based technology, that's essentially a core organic structure, which is a PCB essentially, which is basically merged with an RDL structure. So basically you're obtaining, if you look at the upper cartoon picture, an RDL fan-out structure that fan out underneath the PCB structure with the die sitting within that PCB. And the vertical connection is essentially going through that PCB structure. Okay, one more slide before we look at the detail of that. So I'm bringing back this typical process flow, which says fan-out wafer level, but this is also applicable for the fan-out panel level. So what I want to point out here is that the Samsung PLP is using a phase-down process, which is, again, to recap, that the active side of the dies are facing the carrier. So let's keep that in mind when we look at the section view. So this new package was observed in the Galaxy Watch from Samsung. So this is looking at the backside of the watch. There's a small PCB inside, and this is where we found the POP assembly. So similar to the TSMC Info POP, it consists of a DRAM package, which is mounted on top of, in this case, it's an Exynos 9110 application processor package. And that's the one, I mean, the bottom package, which is using the PLP technology. Package image from top and bottom images. So it's a fairly small package, 8 by 9.5 millimeter. On the bottom side, there's, I think, roughly about 630 some solder balls at a pitch of 0.35 millimeter. So pretty fine pitch deposition here. Okay, first cross-section view. So similar to the TSMC approach, we have the upper image is the overall section view, and we'll be looking at a specific area. So in this case, we're looking at the left side, the middle portion of the assembly, and the right side. So the DRAM package is visible here, which is mounted on top of the Exynos 9110 package, which is this PLP structure. So what we have in this PLP structure, so first of all, there's two die in this package. So there's the application processor die where my cursor is, and the PMIC die. So if you look in the overall section view, that's a PMIC. Oh, my cursor doesn't show up, eh? Sorry, I think that the cursor was showing up, but it's not showing up. So below that, the application processor die, what we could see is the front side RDL, which is running below the dies. On top of this, we have the embedded PWB. So the embedded PWB, again, is running from left to right, so it's visible in each of these images. So the white material above the PMIC die and the application processor die is basically an overmold material. So what's new here is what we can observe is a backside RDL, which runs on top of the package. So that's something fairly new here. Okay, so let me step back here. So what I just brought up here is these two vertical red lines. So I'm just boxing the package edge or the bottom package edge, and the green line is basically boxing the DRAM package edges. So I'm just trying here to understand if the mounting of the POP was done at the panel level or if it was done as a post-process. So as you could see, the DRAM package edges are not collinear with the PLP structure underneath this. So that essentially is telling us that the mounting has to be done after the dicing process, most likely. I mean, there's no firm observation on that, but that's what I believe happened here. Moving down to the next slide. So what we're showing now is a bit more detail about the structure. So on the left side, what we see is the application processor die, and the PMIC die is on the right side image. So these two images again are the same, exactly the same magnification. So I've just brought up this reference line, this red line here, which we'll talk a bit more next on that. So below that reference line, what we have is basically the front side RDL, which consists of 3 RDL layers. So below that, we see a bottom and encapsulation material, which is this white structure. Through that, we have some via connection that essentially connect to the very bottom metal structure. So essentially, we have 4 RDL layer on the front side. Above that reference line, the embedded PWB is visible. The top encapsulated material, which encapsulate the PWB along with the dies, visible. And on the very top side, what we call the backside RDL structure with via connection down to the embedded PWB. So back to that reference line, I guess the idea here is to find out if this process is the Samsung process is using a face-up or face-down process. So as I mentioned earlier, I said that not TSMC, but Samsung is using a face-down process. So what I'll show in the next few slides is along that reference line, there's no planarization process that happened. So that's one element. Second element is the backside of the dies. Well, the application processor die backside and the PMIC dies are not at the same level. So again, there's no way that the backsides were mounted on the carrier at some point. So it means that this reference line is actually the starting point of the whole process. So the carrier used in the making of this product was below that reference line. Okay, moving down to next section view. So what we're looking at is the center area of the package. So let me bring that reference line. So again, below that reference line, we see the front side RDL. So let me step back here. We actually start seeing the application processor die corner on the left side and the PMIC die on the right side. So the embedded PWB is in between that. So now we're seeing how Samsung does the vertical interconnection between the front side RDL all the way up to the DRAM package. So instead of using through-mold via, so these guys are essentially using this embedded PWB with, in this case, stacked via that makes the connection from the very front side of the RDL structure all the way up to the back side. So by the way, we've seen cases through through some other cross section where it's not a perfectly vertical stacked via, but it's a staggered connection all the way up to the RDL structure. So that's a nice feature. So if we were to delayer that package, so just to give you some feeling of how this whole thing is put together. So this is what you'll be observing. So basically the entire printing wire board, the PWB is visible with the 2 dies sitting side by side. So this tiny web of PWB is what's being shown here in the middle where my cursor is, with the PMIC die on the right side and the application processor die on the left side. So basically there's cavities, openings where these 2 dies are dropped down inside these openings. Okay, next slide is looking at some nice images of the application processor die corner and the PMIC die. So by the way, these 2 images are not at the same magnification, but the reference plane, this red line is at the same level. So the application processor die, 94 micron thick, and the PMIC die is 90 micron in thickness. So the overall package thickness in this case is 240 microns. So if we look at the left image, so new features here that we're revealing is what we call the pre-pattern UBM. So this structure was actually pre-patterned on top of the application processor die prior to the integration into this panel level structure. Similarly, for the PMIC die, as labeled here, we have a PMIC pre-pattern RDL. So same approach here. So the structure was pre-patterned on top of the PMIC die prior to the integration. the panel level assembly. Okay, so next slide, we're looking at the very highly magnified view of the two corner of, well, the application die on the left side and the PMIC die on the right side. Same magnification view. So let me bring again this reference plane. So what's visible is the top encapsulated material that runs under the die. So if you were to magnify and along that surface, you will not be observing any planarization process taking place here, as I mentioned before. So what's visible on the PMIC side, we start seeing the pre-pattern RDL, which we'll see more detail in the next slide. So I guess looking at the front side RDL, so the smallest trace width observed on this design was 7 microns. So pretty small trace on a pitch of basically a 15 micron pitch. Overall RDL thickness, 5 to 6 microns observed along this full structure. Okay, a bit more detail about the interconnection of this RDL structure down to the application processor die on the left side and the PMIC die on the right side. Again, these two images are the same magnification, so we can compare them side by side with that reference line. So the pre-pattern UBM is visible on the left side image with this nice connection. So the M1 copper RDL that via down and connects eventually to that UBM structure. So looking on the right side, the PMIC pre-pattern RDL visible, which also comprise this dielectric, the dielectric 2 structure is part of that pre-pattern RDL. And as you can see, there's kind of a wavy pattern. So let me bring another animation to it. So that's the topography of this dielectric material. And clearly we can see that it hasn't been planarized prior to the integration or after the integration into this panel level structure. Okay, now we're looking at, on the left side, a bit more detail about the PMIC die and the middle section where we see the embedded PWB with the RDL structure, the front side RDL structure. So these two images are the same magnification. So looking at the left side image, so the PMIC pre-pattern RDL is really visible here with some nice connections to the front side RDL via down and connects to that pre-pattern RDL. So that's a nice section view here. So one point that I want to talk about is this top encapsulation 1 and top encapsulation 2 layer. So let me bring a few arrows here. So these arrows is pointing basically to an interface line between these two layers. So on the left side image, it's not that much visible, but we could actually see the same interface in between these two encapsulation material or layer. So let me bring a reference line to that interface. And now I've just brought up a second reference line, so I'm just boxing this top encapsulation 2 material. So focusing on the very bottom structure, we also see another encapsulation material on the very bottom of the package, which is also boxed by this green layer. So one point here is that the thickness of these two top and bottom encapsulation or molding compound is essentially the same. And I'll walk you through the process step in the next few slides. So this is a key point to understand that these two layers were part of the process in the making of this whole structure. Another nice cross-section view that shows the overall layers involved in this package structure. So we're looking at the left side of the package and the right side of the package. So the overall thickness is 235 microns, as I think I mentioned earlier. So all the layers visible with the dimensions. Again, the top encapsulated interfaces is visible with these arrows pointing to that, and boxing the top encapsulated structure. Okay, now that I think we have a fairly good understanding of the structure, let's go through the specific process steps involved in the making of this structure. So like we've done with the TSMC info, let me bring the reference line, since this is a phase down process, so that reference line is important since it's the starting point of the making of this package. So let me blank these two images and bring the panel carrier. So we're now ready to start and bring back some of these images. So on the right side, the PMIC die has been unblanked, so the PMIC die is facing down the panel carrier. So obviously there's a lot of dies sitting on that panel carrier at that point. The embedded PWB, well, it's not embedded yet, but it will be in a moment. So this PWB was also deposited or attached down to that panel carrier along with all the dies. So next step is to overmold this entire panel carrier, which overmold the PWB and overmold the PMIC die and all the other die, the processor die for that matter. Next step is to remove the panel carrier. So we're now ready to pattern the fronts, what I call the front side RDL. So the three layers are patterned underneath that whole structure. Next step, so I just brought up the top encapsulant layer and the bottom encapsulant layer. So these two process steps, I've shown them as being sequential, but likely they were done in one single overmolding process, top to bottom. That's an assumption here. So once we have this, we need to drill through that molding compound, well, laser drill, to actually form the hole so that we can actually via down to that structure. Similarly, on the bottom side, we have to laser drill through the bottom encapsulant to make the hole for the connection to the front side RDL. So we're now ready to pattern the backside RDL, which via down to the M1 copper from the wiring board. And similarly on the backside, or the front side, I should say, we can pattern now the M4 copper layer. Solder mask deposition on the top, and finally, solder ball attachment. So again, these are probably the process steps or the major process step used in the making of this package. Okay, next step is to go through the planar view of the Samsung PLP assembly. So we're looking down at the very bottom structure, so the M4 copper layer. Essentially, we have a bunch of ball lands with some interconnection going on between these lands. Next layer down, well, that's the intermediate layer. So we're looking at a VL layer. So between the solder ball lands and the M3 layer. So what I want to bring up here is for every single solder ball connection, there's 4 via piercing through the molding compound. So that's the front side RDL M3 copper, essentially a bunch of mini planes with some trace connection going on that layer. That's the M2 copper layer. So let me bring some highly magnified view of a portion of that structure. So we see some some fat trace with likely some power planes and ground planes going on that structure. Frontside RDL M1 copper. So that's essentially where most of the interconnection is going on. So we can start seeing in the background the application processor die on the left side and the PMIC die, if you follow my cursor, on the right side. So if I bring a highly magnified view of this, we can see some nicely laid out differential pair. Next layer up, so we've basically reached the the starting point of the process. So we got rid of all the fan out structure. So what we're exposing now is the embedded PWB, which is visible, along with the looking down at the die structure. So as you can see on the right side, the PMIC die, so the pre-pattern RDL is now clearly visible, which is brought up here on the left side image. So again, that structure was pre-deposited on the PMIC die prior to the integration into this panel level structure. Next layer up, we're looking at the M2 copper from this embedded PWB. So essentially likely a ground plane with some traces interconnection going on. Next layer up is the M1 copper. And finally, we're looking at the backside RDL structure. So there's still some white material, which is essentially some molding compound remaining on that layer. So the good thing about that is that we see these little dots. So those dots are basically the via connection down to that backside RDL structure. So essentially there's a bunch of via running, well, essentially, if I bring back the previous image, running to that little web in between the two dies. So this is where the some of the vertical connection is made, along with some vertical interconnection on the periphery of the package. And you can see some of these traces in the middle that connects eventually all the way along the perimeter of the package, where the DRAM solder balls will be connected to from the upper package. So that's a highly magnified view of that structure. Okay, it's time for a quick conclusion. So TSMC info and Samsung PLP. So what we've seen again, first one is a wafer level base package. The second one is a panel level base package. POP mounting for the TSMC info was done at wafer level. For the PLP structure, it was likely done as a post-process. RDL processing, so die first face up for the info and die first face down for the PLP. MCM compatible, so MCM stands for multi-chip module or multi-chip package. So for the PLP, it's confirmed. We've seen two dies sitting side by side interconnected with this PLP technology. For the info, well, we haven't seen that yet, but the structure is basically designed for multiple die application as well. Looking at the key features, overall package thickness 230 versus 240 microns, pretty much the same in my opinion. In terms of RDL layer count, for the info we have 1 plus 4, so 1 pre-pattern RDL plus 4 fan-out RDL. Similar thing was observed on the PLP, but in this case we have a backside RDL as an additional features for routing all your signals and all that. So that's, in my opinion, a big plus for the PLP structure. Vertical interconnection to the POP. So TSMC is using through mold via, so it's a single vertical connection from point A to point B. TSMC is using a combination of this embedded PWB with multiple routing layers, and so they could use stacked via connection, or they could use also staggered via connection all the way up to the POP. So that's a big plus also, in my opinion. Frontside RDL thickness, trace width, and RDL trace pitch, again, very similar features, plus minus 1 microns. One thing that we haven't touched base on is the overall cost to produce these two packages. So like we've seen before, the whole motivation to move to the PLP, or the panel level structure, is to reduce costs. So is the Samsung PLP really cheaper than the TSMC info process? Well, we don't have any specific data on this, and someone needs, I guess, to do some detailed cost analysis. But as we've seen, the PLP technology requires a lot more process steps and also additional material like this embedded PWB. So this certainly offset the saving provided by the PLP approach. So that's basically conclude my presentation for today.
Hello, my name is Cameron McNeil. I'm a packaging analyst here at Tech Insights. And just to follow up the presentation we just watched, I want to quickly update you on where we are with fan-out wafer-level packaging and panel-level packaging since 2019 when the recording was originally made. So then I'll also quickly give you some of my thoughts about what the future of fan-out packaging is in relation to the recent advancements we see in advanced packaging, and talk a bit about what the future of this technology might be. So what's happened since that original recording? So in the wafer level space, and with wafer level fan-out packaging, the TSMC info technology is still the sort of baseline, what Apple is using in its mobile processor packages. So on the channel you'll see the A15, and then the A16 is actually being analyzed and is going to be published to the platform, I think just in a day or two. And both of those devices use a structure that's almost identical to the A11 as we just saw it presented in the 2019 recording. So that's that structure with a memory package above, a processor package below, vertical interconnect with a BGA and through molding vias, and then at the bottom of the processor package, the TSMC info fan out. To go in and pick up the die level pitches of the flip chip device and bring them to the outside world. So it's not just the A series, it's also the S series. So the S series are Apple devices that are used in the Apple Watches in the wearable category, and those devices are also using TSMC info POPs. So the actual S7, you'll find the S7 on the channel, but also the S8, which is being analyzed now, are larger modules that integrate power and all kinds of other functionality together. But one of the things that's integrated in the S modules is an TSC info POP package, directly analogous to the A series packages. And in some of those, for example, the S7, the bottom package, the processor package in the POP, is a multi-die package. So it uses TSMC info RDL in a wafer level technology, but there are multiple die in the bottom. Now, in the case of the S7, the second die is actually a blank silicon die that's there likely for mechanical reasons. To maintain stability, they need to fill up more space based on the size of the memory package above. They need to have more silicon in there to get things to balance. But we do actually see multi-die fan-out wafer-level packages from other manufacturers, from other OSATs, and wafer-level technology is actually quite good at forming an interconnect between two different die, and then also taking those signals and connecting them to the outside world. And the last thing to say here is that TSMC appears quite committed to the wafer level technology as opposed to panel level, and I think there's no surprise there. TSMC, is leveraging their experience with wafer technology and their foundry experience, and they have something that works quite well. They're building good products for industry leaders. I think this is quite logical. In the panel, speaking of panel level, so with panel level fan-out packaging, there's been a continued development towards sort of prime time production since 2019, and so we now see multiple offerings, not just the Samco/Samsung offerings that my colleague just presented, but also from other OSATs. If we review ASE's public material, you'll see that they're offering technologies down to 2-micron lines, so that goes back to the ability of fan-out technology to go in and really pick up the die level pitches. And but we also see offerings, Deca's M series technology. We see things from Power Tech, and then also NEPS. So NEPS is a large OSAT of offering, or they just opened a panel level facility about a year ago at the end of 2021 with an advertised yearly capacity of almost 100,000 panels. And take that in conjunction, that high volume in conjunction with the fact that the sort of the stated advantage of panel level packaging is to operate at the panel level much larger than the wafer level. And so this is a significant volume of devices here, and that's just from one party. I believe NEPS for that facility is actually licensing Deca's M series technology. So that's all to say that panel level packaging is continued to go forwards and become an industry, a tool of the industry, and the industry is looking to continue that. So the Fraunhofer Institute is overseeing what's called the Panel Level Packaging Consortium 2.0. So this is focused on technical challenges. Building these large panels, there are technical issues as you begin to filling the panels with silicon. They can warp, they can bow, there's CTE problems, there's alignment and registration problems. And all these things are exacerbated as the panels grow and the density of silicon increases. But there are also operational challenges or risks associated with these strategies, right? So the more die that you put in an individual panel, the more that's at stake or at risk in the case of a panel crash, or of a line crash or rework or something like that. So the industry is, I think, exploring all of this and finding out what works for individual companies, individual products, and feeling their way through that. So panel level technology. I want to highlight sort of here the panel level device that was shown in the 2019 recording is obviously structurally different from the wafer level device, but that is not necessarily the case. A panel level process should be able to produce something that is similar in structure to a wafer level process, and so it's something we all have to keep in our minds when we're looking at devices, and sometimes it's necessary to move beyond the physical analysis of a device when we're trying to determine a difference between a wafer level or a panel level fan-out package. So what's coming next for fan-out packaging, both of either or wafer or panel? So so first, what's driving the developments in advanced packaging, and it's quite clearly heterogeneous integration. So how can we integrate multiple die into a system without you know, keeping the advantages of an IC, integrated circuit. You know, so so more importantly, the question today is, what role would or can fan-out packaging have in heterogeneous integration? So there's a few things, sort of starting at the beginning. There's a few things we know fan-out's good at, right? We've talked just a moment ago about multiple die integration, so we know it can create a die-to-die interconnect, and we also know that it's because it's not based on traditional printed wiring board technologies, but rather comes sort of out of wafer processing and is really an RDL process. The interconnect is, then it's able to create these very dense pitches and go in and pick up fine pitch pads right on the die. So we kind of have a case study here that would like to expand on in the future, but you can find the report on it in the channel right now, and that's the M1 Ultra. So that's a desktop processor from Apple's Mac Studio desktop machine. And it's effectively, what happens inside of the M1 Ultra package is that two discrete processors, and we can actually see them in this little image here on the left and the right, processor 1 and processor 2 are joined together by a packaging system to create what is effectively a single, very large, very powerful processor. And so, you know, we talk a lot about the silicon bridge that provides the ability to connect those two devices together, but actually, in the TSMC info RDL is actually part of the fabric that ties this whole thing together. So, you know, we can just kind of make out the bridge in this low mag image here on the slide, sitting very thin. It's sitting down between those, underneath those two processors. But above that bridge and below that bridge are multiple layers of TSMC info RDL, and you know, they're integrated with that bridge in a way that creates what TSMC calls their integrated fan-out local silicon interconnect. So they add a bridge. They're effectively making a wafer level fan-out package, but with an additional layer on top that is this bridge. And so the pitches are very fine in these, the processor to bridge interconnect. It's like a 25 micron pitch or something like that. And so fan-out technology has the ability to go in and operate at that level. So the future is kind of rosy for fan-out technology. It's actually forming the basis of some of these advanced packages. There are other devices that we're analyzing right now, and reports will be available in the new year, where other OSATs are creating similar or competing technologies. So you can stay tuned for that, and we hope to have more information about these advances in packaging in the new year. We can talk more in detail about the M1. And how fan-out technology is being used in these other devices. So with that, thank you very much, and I'll be answering questions afterwards. Thanks very much. Okay, thanks everyone for coming. This is the live Q&A session after the pre-recorded presentations. So if you have questions you'd like to ask, please go ahead and enter them using the using the interface for the webinar software, and I'll read out the questions and answer them. So we have a question here that's come in about the structure of the through molding vias. So going back to the A11 that was presented by my colleague, there we saw that the through molding vias, the TMVs, are fully filled with copper. So those vias are not hollow. We haven't found evidence of voiding inside of them. So it's always difficult to be certain of that in cross section because you're only seeing one slice. But in the delayering images, we get a few slices vertically as we move through them, and we don't see voids. So my colleague was speculating about how those TMVs are created, and he talked about the possibility that they are essentially a pre-built structure, something like a lead frame that's put on the carrier alongside the die. So I get the privilege here of having a bit more information just from seeing another part, which is the M1 Ultra I was just talking about. That device also features TMV-like structures, and in that part, there's some evidence that the ones in that device are actually plated. But in principle, they serve the same role and are also solid copper. So there's another question here about asking me to comment about why the panel level technology is not sort of as widespread yet in industry as the wafer level technology. So I think you sort of covered a lot of my thoughts. You know, there are additional processing steps which counteract some of the potential for cost reduction that come from the volume, the area sort of justification for panel level packaging, where you can process many parts in parallel at the same time in the same lot. And so those extra processing steps counteract some of that and eat into the advantage that way from a business perspective. And then there are also those operational risks that I alluded to, with, when you have potentially more, the output of, when you potentially have so many die in one panel, you might have, it's conceivable that you actually have more than one wafer's worth, right? You might have multiple wafers worth of die tied up in a single large panel. These panels can be like 18 by 24 inches. If there is an event where rework is needed or there's a line crash, it's a lot of eggs in one basket, as to use an expression. And I guess the other thing to say about wafer level and panel level, fundamentally, they produce structures that serve the same role, or from a product design perspective. There are minor differences, but effectively they're competing for the same design space, as it were. And in that, companies who are doing the work, there's a bias. If you are fundamentally a wafer fab and you have a lot of, you're tooled up to work on wafers, the wafer level reconstituted wafers fan out technology is appealing to you. If you are a manufacturer of organic substrates and you build PCBs and printed wiring boards, you're positioned to move into the panel level space. And so I think that these technologies have come out of companies doing packaging, which tends to be more closely related to the wafers and foundries than it is some other companies that are sort of climbing down the chain from organic substrates down into actual packaging. So another question about panel level packaging: does it require planarization, or will we get to a point where it needs planarization? So, as was shown in the presentations, the device, the Samsung device doesn't really show planarization evidence. Personally, I'm not aware of planarization processes being used in the manufacture of traditional organic substrates. So I think it's a big hurdle to clear. Perhaps it would have some advantages, but like I said, I think it's sort of would be a big next step. I'm not sure exactly what the tooling would look like. Okay, so other question about are these technologies are these technologies, these fan-out technologies, going to be replaced? So obviously I was just saying they're competing with each other a little bit, but fundamentally, I mean, packaging technologies stick around for a long time typically, and I think fan-out technologies, and you can take that either as wafer level or panel level, I think both will stick around for a long time. And as I was alluding to in my slides, it seems like fan-out's well positioned to have a space in the future of advanced packaging, and so I think we'll see more of it in the future rather than less of it. It's kind of I think it's a well-positioned technology, but as we know with packaging things, there's still lots of copper lead frame, wire bonded, plastic overmolded packages being built. Packaging technology tends to hang around for a long time. So hopefully we can have an opportunity to show you more of that, some more of the future of fan-out packaging, particularly as it's being used in some of these advanced logic devices that are being analyzed on the channel, like the M1 Ultra, and also competing technologies from some other OSATs. But I think we're pretty much out of time for today. So I would like to sort of wind the webinar down. Thank you very much for coming. Please help to improve this process by completing our survey. That should be available to you now. If you'd like to know more about Tech Insights logic subscriptions, you can email us at info@techinsights.com, or you can visit our website, www.techinsights.com. And thank you everyone for your participation, and we're looking forward to talking to you next time. Have a great day.